When you look up at the night sky, all the stars you can see are part of our galaxy, the Milky Way. Scientists estimate that the Milky Way is home to between 200 and 400 billion stars. This is hardly surprising, given that the Milky Way is around 100,000 light-years long and 1,000 light-years thick. And yet, the Milky Way itself is just one of some 2,000 billion galaxies in the observable universe, enough to make you dizzy. Our galaxy is part of what is known as the Local Group, a group of over 50 galaxies whose diameter reaches 10 million light-years. Together with the Andromeda Galaxy, the Milky Way is one of the two most massive galaxies in the Local Group. These two spiral galaxies are separated by around 2.5 million light-years, but as they approach each other, at speeds of over 400,000 kilometers per hour, they are set to collide in around 4.5 billion years. Although impressive, this collision should pose no danger to our planet. From Earth, the sky is a magnificent starry spectacle that this new giant galaxy will form. Dear traveler, welcome. Today we're going to set off together to discover the Local Group, made up of the galaxies closest to us, located just a few million light-years away, rather than several billion, so we can consider them our neighbors. In fact, some of them can be observed with the naked eye. On this journey to the heart of the Local Group, you'll be able to observe the dipolar structure of this grouping of galaxies. Seen from here, the Local Group looks a bit like a dumbbell, with the Milky Way and its satellites on one side and the Andromeda Galaxy and its satellites on the other. Together, we're going to explore the two main galaxies of the Local Group, the Milky Way and the Andromeda Galaxy, as well as all the smaller galaxies concentrated around them. On this journey, you'll discover just about every type of galaxy there is, from spiral galaxies to dwarf galaxies, with spherical, elliptical, or even square shapes. But before you set off on your next adventure, make sure you like the video and subscribe to the channel so you don't miss a thing. Thank you, and fasten your seatbelts for immediate takeoff to discover our neighboring galaxies. We're on our way to the Local Group. We've got a long way to go, since just to get out of the Milky Way we'd need thousands of light-years. In the meantime, let's take a look at the history of the Local Group. Where does the term Local Group come from? The first to use it was the German astronomer Walter Bode in 1935 in a publication about the globular cluster NGC 2419, or Caldwell 25. For the record, this globular cluster is located in the Lynx constellation, some 300,000 light-years from us. It's nicknamed the Intergalactic Vagabond, as it seems to have belonged to the Milky Way before, but eventually broke away from it. NGC 2419 is also part of the Local Group. The term Local Group was coined in 1936 by the American astronomer Edwin Hubble, after whom NASA's famous telescope is named. Edwin Hubble developed Hubble's law, according to which galaxies move away from each other at a speed roughly proportional to their distance. In other words, the further away a galaxy is from us, the faster it seems to be moving away. This law was the first proof of the expansion of the universe, stating that it is not the galaxies, planets, and stars that are moving, but the space between them that is increasing. In the 1930s, when the local group concept first emerged, not so many galaxies had been discovered. Edwin Hubble first counted just a few galaxies in the local group. The Milky Way and the Andromeda Galaxy, of course, but also the Large Magellanic Cloud, the Small Magellanic Cloud, M32 NGC 205, the Triangulum Galaxy, Barnard's Galaxy, and IC 1613. The local group concept was later used in a publication by American astronomer Walter Body in 1944, in which he established that the galaxies NGC 147 and NGC 185 belong to the local group. It was Body who brought the number of galaxies in the local group up to 18 by adding a few more to the list: the Dragon, Furnace, Leo 1, Leo 2, Sculptor, Little Dipper, and IC 5152 galaxies. The IC 5152 galaxy was subsequently excluded from the local group galaxy list, however, as it is too distant, at 5.8 million light-years from us, to belong to our group of galaxies. During the second half of the 20th century, other galaxies were discovered and added to this list, notably dwarf galaxies. A dwarf galaxy is a small galaxy made up of 100 million to a few billion stars. By comparison, the Milky Way contains 200 to 400 billion stars. Dwarf galaxies often orbit larger galaxies, as is the case in the local group, where we find dwarf galaxies concentrated around the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy, the three largest galaxies in the local group. Over 30 dwarf galaxies have been identified, orbiting our Milky Way galaxy, including the Large Magellanic Cloud, the largest, and the Carina Dwarf Galaxy, the smallest. In 2000, there were officially 38 galaxies in the local group. Today there are over 50. It's hard to say with any certainty how many galaxies are in the local group. Not only can't we detect all the galaxies, because some are much less luminous than others, but we still don't really know where the local group ends. What we do know today about the local group is that it is built around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. Surrounding the Milky Way are the two Magellanic Clouds and many other galaxies whose names may be familiar to you: the Big Dog, Sagittarius, Little Dipper, Dragon, Carina, Sextant, Sculptor, Furnace, Leo 1, Leo 2, and Toucan galaxies. Surrounding the Andromeda Galaxy are the galaxies M32, the Triangulum Galaxy M33, M110, NGC 147, NGC 185, and Andromeda 1, 2, 3, and 4. The Triangulum Galaxy also has a satellite galaxy, the Pisces Dwarf Galaxy. On this journey to the heart of the local group, we'll be taking a closer look at each of the main satellite galaxies of the Milky Way and Andromeda galaxies. But when we talk about satellite galaxies, we don't mean that they're completely glued to the galaxies around which they orbit. To give you an idea, the Great Dog Galaxy, the closest satellite galaxy to the Milky Way, is located 25,000 light-years from our galaxy. Apart from the two main galaxies and their satellite galaxies, the local group also includes galaxies independent of these subgroups, which we'll be observing at the end of our journey to the far reaches of the local group. We've now reached our destination. It's time to take a closer look at the local group. The local group is located at the edge of a giant supercluster of galaxies, the Virgo supercluster. Also known as the local supercluster, the Virgo supercluster is a supercluster of galaxies comprising the local group, and at its center, the Virgo cluster. It comprises around 10,000 galaxies, and much of its mass is probably dark matter. As the universe expands, the local group is moving away from the Virgo cluster, and therefore from the center of the Virgo supercluster. The local group extends over a diameter of around 10 million light-years. It contains every type of galaxy except giant elliptical galaxies, which are not found in such small structures. That's right, because the local group, despite its 10 million light-year diameter, is not considered a large structure by comparison with other galaxy superclusters. We can't know the exact number of galaxies in the local group. Some are too faint, others are obscured by the Milky Way. Depending on the source, you may hear talk of 60 or 80 galaxies. In any case, there are more than 50. In the local group, there are 3 spiral galaxies: the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. Spiral galaxies account for 3/4 of the galaxies listed in Hubble's classification of galaxy types, developed by Edwin Hubble in 1936. Their structure is particularly complex compared to that of elliptical galaxies. Spiral galaxies consist of a flattened disk containing a few 100 billion stars and a luminous spherical central bulge known as the bulge. 2 or more luminous arms extend from the disk, spiraling around the bulge. The center of the disk rotates faster than the edges. Barred spiral galaxies like the Milky Way are distinguished from ordinary spiral galaxies. Barred spiral galaxies have a linear structure instead of 2 spiral arms. Spiral galaxies also contain a lot of gas and dust. The arms of a spiral galaxy are made up of these gases, as well as the youngest and brightest stars. Scientists believe that spiral galaxies have this spiral shape at the beginning of their lives when they contain a lot of gas, and then gradually lose their rotation and become elliptical as galaxies merge. The local group also contains 2 Magellanic spiral galaxies, the Large Magellanic Cloud and NGC 3109. This type of spiral galaxy has only 1 spiral arm and is smaller than an ordinary or barred spiral galaxy. Only 1 elliptical galaxy has been identified in the local group, M32, which is a satellite of the Andromeda Galaxy. Elliptical galaxies differ from spiral galaxies primarily by their elliptical shape, but not only. Unlike spiral galaxies, they don't contain a gas disk where young stars can form, and the movement of stars is random, whereas in spiral galaxies, stars are in rotation. Elliptical galaxies are made up of old stars, which is why scientists believe they form when 2 spiral galaxies collide. In the local group, M110 and NGC 147 are dwarf elliptical galaxies, a type often found in galaxy clusters and often companions to other larger galaxies. The majority of local group galaxies are spheroidal dwarf galaxies, galaxies that are more or less spherical in shape and small in size, i.e., with a few million to a few 100 million stars. Spheroidal dwarf galaxies are ancient and have evolved very little, and their composition resembles that of globular clusters. very dense concentrations of spherical stars orbiting galaxy nuclei. Finally, the rest of the local group are irregular galaxies. These galaxies show no regular structure, being neither spherical, elliptical, nor spiral-shaped. Most irregular galaxies are dwarf galaxies, rich in bright stars and therefore very luminous. Even so, they are difficult to detect because of their small size. Scientists believe that this type of galaxy was once very common in the universe, but that collisions reduced their number. Today it is estimated that at least 10% of all galaxies are irregular. We're now going to take a closer look at each of the main galaxies identified as part of the local group, from the galaxy closest to us to the most distant. The Milky Way, our galaxy, is the second largest galaxy in the local group. It's also known as the galaxy with a capital G. It's a spiral galaxy, home to between 200 and 400 billion stars, including the Sun, and probably over 100 billion planets. The Milky Way's diameter is estimated at 100,000 to 120,000 light-years, perhaps even as much as 200,000 light-years. The center of the galaxy is a supermassive black hole, Sagittarius A, and the solar system is located 27,000 light-years from this center, so it's more on the periphery. Stars revolve around the center of the galaxy, and the Sun takes around 250 light-years to complete a full circle. Since it came into being, the Sun has made only about 20 revolutions. You may be wondering why our galaxy is called the Milky Way. When seen from the sky, the Milky Way looks like a white streak, like a milky flow of stars. In Greek mythology, the origin of the Milky Way is explained in an imaginative way. The Greeks recounted that Zeus had had an illegitimate child, Heracles, with his mistress, Alcmene. Zeus, wishing to make his son immortal, took advantage of a moment when his wife Hera was dozing to lay the infant Heracles on her breast. He begins to suckle Hera, but she wakes up and realizes that this is not her real child. So she forcefully pushes him away, leaving a trail of milk in the sky that will become the Milky Way. The Milky Way has also often been likened to a river. The Egyptians thought it was a copy of the Nile in the sky. The Chinese called it the Silver River, and the Japanese the River of Paradise. This idea of a river in the sky can be found in several Asian mythologies. Lastly, it could also have religious connotations, as was the case with the Mayans, who believed it to be a religious path, enabling souls to reach paradise. In 1610, Galileo was the first to show that the color of the band formed by the Milky Way in the sky was due to the presence of numerous stars. It wasn't until the 1920s, however, that Edwin Hubble proved that the Milky Way was just another galaxy. In the 1930s, the Milky Way's galaxy model was established, a barred spiral galaxy. The Milky Way has 6 spiral arms, which in turn divide into other spiral arms: the arm of Perseus, the arm of the ruler, the arm of the swan, the arm of the cross, the arm of Sagittarius, and the arm of Orion. Our solar system is located in the Orion arm. If the Milky Way appears to us as a flat disk in the sky, it's because we see it from the edge. According to researchers, our galaxy was formed by the merging of several dwarf galaxies that appeared 800,000 million years after the Big Bang, during a phase of very active star formation. There are many different types and ages of stars in our galaxy. In fact, the oldest star in the Milky Way, HE 1523-0901, is 13.2 billion years old, so it appeared shortly after the Big Bang. This is the scenario that has so far been accepted to explain the formation of the Milky Way. 13 billion years ago, two galaxies began to form stars independently of each other. On one side was a dwarf galaxy, Gaia Enceladus, and on the other, a galaxy 4 times more massive and richer in metals. 10 billion years ago, these two galaxies collided. Some of their stars were ejected into chaotic orbits, forming the Milky Way halo. For 4 billion years, violent episodes of star formation followed one another, until around 6 billion years ago. The remaining gas settled into the Milky Way's disk, which we can still observe today. Surrounding the Milky Way are orbiting dwarf galaxies, including the Small Magellanic Cloud and the Large Magellanic Cloud, which are visible to the naked eye from Earth in the southern hemisphere. The Great Dog Dwarf Galaxy is the closest known satellite galaxy to us. It is located in the Big Dog constellation, 42,000 light-years from the center of the Milky Way and 25,000 light-years from our solar system. It is an irregular dwarf galaxy and contains 1 billion stars, equivalent to 1% of the Milky Way. It was discovered rather late, in 2003, because it lies behind the plane of the Milky Way, where clouds of gas and dust are denser. However, this galaxy may no longer exist in the future. The tidal forces of the Milky Way are tearing it apart. At present, the center of the Great Dwarf Dog Galaxy is badly degraded, with a long filament of stars trailing behind it, 3 times around the Milky Way. This filament of stars is sometimes referred to as the unicorn ring, and it was this filament that enabled scientists to discover the Great Dwarf Dog Galaxy. Let's continue a little further. 80,000 light-years from Earth and 50,000 light-years from the center of the Milky Way lies the dwarf Sagittarius galaxy. This galaxy is thought to be elliptical or spheroidal, and should not be confused with the irregular Sagittarius dwarf galaxy. In fact, we don't know whether it's spherical or elliptical, as it's being stretched by the tidal forces of the Milky Way. The Sagittarius dwarf galaxy was discovered in 1994. At the time, it was the closest known galaxy to our own. It too is rather difficult to observe, as it is diametrically opposed to the solar system in relation to the center of our galaxy. Spectroscopic analyses have shown that this galaxy is probably very old. It is made up only of old metal-poor stars, known as Population 2. Scientists predict that it will eventually be absorbed by the Milky Way. A little further on, the Large Magellanic Cloud is a barred Magellanic spiral galaxy. With a diameter of 14,000 light-years, it is the 4th most massive galaxy in the group, after the Andromeda Galaxy, the Milky Way, and the Triangulum Galaxy. The Magellanic Spiral Galaxy is a type of spiral galaxy with a single spiral arm. This type was coined for the Large Magellanic Cloud by French astronomer Gérard de Vaucouleurs when he revised Hubble's classification. Unlike the other two satellite galaxies we've seen so far, the Large Magellanic Cloud can be seen from Earth, more precisely from the southern hemisphere. In fact, it was discovered much earlier than the Great Dog and Sagittarius dwarf galaxies, since it was first mentioned in 964 by a Persian astronomer by the name of Abd al-Rahman al-Sofi. The Large Magellanic Cloud could collide with the Milky Way long before the Andromeda Galaxy. It is home to some remarkable celestial objects, including the Tarantula Nebula, a region of ionized hydrogen, or HII, and the largest nebula known to date. In this zone, the star birth rate is higher than in any other region of our galaxy. The Large Magellanic Cloud also contains stellar black holes, celestial objects created by the evolution of the most massive stars after their supernova explosion. There's also a soft gamma-ray star, SGR 0526-66, a source of gamma rays that is probably linked to young neutron stars with strong magnetic fields. The Large Magellanic Cloud is linked to the Small Magellanic Cloud by a bridge of gas and stars called the Magellanic Bridge. The Small Magellanic Cloud is an irregular galaxy located in the Toucan constellation and is one of the most distant celestial objects visible to the naked eye. However, like the Large Magellanic Cloud, with which it forms a pair, you can only see it from the southern hemisphere, far from light pollution. Like the Large Magellanic Cloud, the Small Cloud was first mentioned by navigator Amerigo Vespucci in a voyage report from 1503 to 1504, but it was Magellan's expedition that gave it its name. The Small Magellanic Cloud is thought to have been a barred spiral galaxy, distorted by the tidal forces of the Milky Way. The Bouvier dwarf galaxy lies close to both Magellanic Clouds. We are now 195,000 light-years from the Sun. This spheroidal dwarf galaxy is located in the constellation du Bouvier, hence its name, and was discovered in 2006. Its luminosity is estimated at 100,000 times that of the Sun, which is very low for a galaxy. The Bouvier dwarf galaxy is strongly disrupted by the tidal forces of the Milky Way. It is composed mainly of very old stars, aged between 13.3 and 13.4 billion years. Let's continue our journey to discover the Milky Way's satellite galaxies. Just 205,000 light-years from our solar system lies the Little Dipper dwarf galaxy, a spheroidal galaxy, located, as you may have guessed, in the Little Dipper constellation. This galaxy was discovered in 1955 thanks to a photographic survey of the night sky carried out at the Palomar Observatory, 80 kilometers north of San Diego, California. Like almost all of the Milky Way's dwarf satellite galaxies, the Little Dipper dwarf galaxy is essentially composed of old stars with little interstellar matter. A little further away, 260,000 light-years from us in the constellation of the Dragon, the Dwarf Dragon Galaxy was also discovered, thanks to photographic surveys by the Palomar Observatory. This spheroidal dwarf galaxy is one of the least visible satellite galaxies because it is so faint. "280,000 light-years away, the Sextant Dwarf Galaxy is a spheroidal dwarf galaxy discovered in 1990. It too is not very luminous and is one of the least luminous nearby galaxies. Just next door, 285,000 light-years away, The Sculptor Dwarf Galaxy was the first spheroidal dwarf galaxy in 1937. Analysis of its composition has revealed that it is similar to the primitive galaxies observed at the edge of the universe. Let's continue a little further afield. There are still more satellites of the Milky Way to observe. The Carina Dwarf Galaxy, 330,000 light-years away, is a spheroidal dwarf galaxy that formed a little more recently than the others. Most of its stars are thought to have formed 7 billion years ago, although analyses have also revealed periods of star formation as far back as 13 billion years ago, and as recently as 3 billion years ago. This galaxy was discovered in 1977 and is around 75 times smaller than our own galaxy, with a diameter of 1,600 light-years. It is moving away from the Milky Way at a speed of 230 kilometers or 140 miles per second. Recently discovered in 2018, the dwarf galaxy Antlia-2 is located 422,000 light-years from us. As you can see, its size is relatively close to that of the Large Magellanic Cloud, but its luminosity is 10,000 times fainter. In fact, it's the least luminous galaxy ever discovered. That's certainly why it was only discovered late in 2018, when most of the galaxies in the local group were already known at the end of the 20th century. The Furnace Dwarf Galaxy is located around 450,000 light-years from us. It is also a spheroidal dwarf galaxy, composed of ancient stars, and shines faintly. Several globular clusters have been detected, including NGC 1049, which is brighter than the galaxy itself. NGC 1049 was discovered a century before the Furnace Dwarf Galaxy. Let's move on a little further to observe the Lion 2 Galaxy, 700,000 light-years away, and the Lion 1 Galaxy, 800,000 light-years away. Both are spheroidal dwarf galaxies. The Leo 1 galaxy is remarkable for containing very little dark matter, compared with the Milky Way's other satellite galaxies. In 2021, a supermassive black hole of 3.3 million solar masses was discovered at its center. We've now arrived at the Milky Way's last satellite galaxy, the Phoenix Dwarf Galaxy. Scientists don't know whether this is a spheroidal dwarf galaxy or an irregular one. Perhaps that's why, when it was discovered in 1976, it was classified as a globular cluster, only to realize a year later that it was in fact a galaxy. This short tour of the Milky Way's satellite galaxies would not be complete without mentioning the Lion A Galaxy, located 2.25 million light-years from us. The problem is that we don't really know whether the Lion A Galaxy is a satellite of the Milky Way or belongs to the group of galaxies known as Antlia-Sextans. We'll be looking at this group of galaxies a little later in the trip, as it's located even further out on the periphery of the local group. Let's continue our journey towards the other galaxies of the local group. We're now 1.63 million light-years from the Milky Way, in front of Barnard's galaxy, or NGC 6822. This galaxy is a barred irregular galaxy. Simply put, it's the irregular version of a barred spiral galaxy like the Milky Way. Barnard's galaxy was so named because it was discovered in 1881 by the American astronomer Edward Emerson Barnard, who also gave his name to Barnard's star. The Barnard Galaxy contains only around 10 million stars, most of them young. Edwin Hubble identified 15 variable stars in this galaxy. Variable stars are stars whose luminosity varies over shorter or longer periods of time. The Sun, on the other hand, is almost constant in brightness, varying by 0.1% over an 11-year cycle. Today, over 150 HII regions have been identified in this galaxy. Previously, it was thought that the universe stopped at 300,000 light-years. The discovery of Barnard's galaxy brought home the true size of the universe. We are now approaching the Andromeda Galaxy, the largest galaxy in the local group, with a diameter of 220,000 light-years. This spiral galaxy is also known as NGC 224, or M31, in the Messier catalog of nebulae and star clusters. This catalog, drawn up in 1774 by French astronomer Charles Messier, was intended to help comet hunters avoid confusing comets with diffuse objects such as nebulae or star clusters. The Andromeda Galaxy is located 2.55 million light-years from the Sun in the Andromeda constellation. Until the 1920s, it was thought to be a nebula rather than a galaxy. It is thought to contain around 1,000 billion stars, 2 to 5 times more than our own galaxy. Its total luminosity would be 26 billion times that of the Sun, or 25% more than our galaxy. But the Milky Way's star formation rate is 3 to 5 times higher than that of the Andromeda Galaxy, and there are twice as many supernovas in our galaxy. Perhaps one day, the Milky Way's luminosity will exceed that of the Andromeda Galaxy. Because it's so luminous, the Andromeda Galaxy is one of the few galaxies you'll be able to observe with the naked eye in the northern hemisphere. If you look carefully, you can't miss it. Its apparent diameter is 6 times the apparent diameter of the Moon from the Earth. In fact, it was discovered a long time ago. The first known written mention of this galaxy dates back to 964 by Abd al-Rahman al-Sofi in his Book of Fixed Stars. However, it wasn't until 1612 that it was observed through a telescope by the German astronomer Simon Marius, the same man who named Jupiter's 4 main satellites, the Galilean moons. The Andromeda Galaxy was first photographed in 1887 by British astronomer and pioneer of nebula photography Isaac Roberts. The Andromeda Galaxy is thought to have formed recently. For astronomers, this means less than 3 billion years ago. At the time it formed, the Earth certainly already existed. The Andromeda Galaxy is thought to be the result of the collision of 2 galaxies. Like the Milky Way, it contains a supermassive black hole at its center, called M31. In around 4.5 billion years' time, an observer on Earth will be able to see the Andromeda Galaxy in the night sky as a pinkish cloud of dust. This is because the Andromeda Galaxy and the Milky Way are about to collide. This collision will have many effects. Firstly, it will cause the collapse of the galaxy's gas clouds. Secondly, it will give rise to new stars. Some stars will be sucked into the black hole, while others will be ejected into intergalactic space. The galaxies, for their part, will merge to form a large elliptical galaxy, their two supermassive black holes will also merge to form an even larger black hole. Around the Andromeda Galaxy, there are also satellite galaxies like those around the Milky Way. The most important of these is the Triangulum Galaxy, or M33, which is the third most massive galaxy in the local group, with a mass 60 billion times that of the Sun. It is also a spiral galaxy. Perhaps you've already heard of this galaxy, home to the fictional planet Vinea in the science fiction comic strip Yokosuno, and the planet Ganesha in Jean-Gaston Vandel's futuristic trilogy. In reality, we don't really know whether the Triangulum Galaxy is a satellite of the Andromeda Galaxy, but we assume it is. The two galaxies are separated by a distance of 750,000 light-years. We are now some 3 million light-years from our solar system. Although the Triangulum Galaxy was first catalogued by Charles Messier in his catalog as M33, it had probably been observed before. Under the right conditions, you can even observe it with the naked eye from Earth, more precisely from the southern hemisphere. In fact, mentions of this object have been found as far back as 1850. The Triangulum Galaxy is a regular, unbarred spiral galaxy, but it does have a bar running 2,600 light-years through its center. At the heart of this galaxy is not a supermassive black hole, but an HII region containing an ultra-luminous X-ray source. ULXs are still enigmatic objects for science. What we do know is that they are ultra-powerful X-ray sources. In fact, the ultra-luminous X-ray source in the Triangulum Galaxy is the most powerful X-ray source in the local group. The Triangulum Galaxy is home to other remarkable celestial objects, starting with several HII regions, the brightest of which, NGC 604, may have undergone a burst of star formation as recently as 3 million years ago. 54 globular clusters have been identified around the Triangulum Galaxy, but there are certainly more than double that number. At equal distance from the Triangulum Galaxy and the Andromeda Galaxy, 2.5 million light-years from us, you can see the Pisces Dwarf Galaxy, or LGS-3. This galaxy could be a satellite of the Andromeda Galaxy or the Triangulum Galaxy, if the latter is not a companion of the Andromeda Galaxy. This irregular dwarf galaxy was discovered in October 1978 in a search for satellite galaxies of M31 and M33. 5 objects were catalogued and grouped together under the name Local Group Suspect, hence the name LGS-3. The Pisces Dwarf Galaxy was the only one of the 5 objects to be confirmed as a local group galaxy. The Pisces Dwarf Galaxy contains old, metal-poor stars, but also atomic hydrogen gas, which may indicate the presence of young stars. It may therefore be a transitional object between a spheroidal dwarf galaxy and an irregular dwarf galaxy. What interests scientists about this small galaxy is the presence of a high-speed cloud called HVC 127-41-330. In this high-speed cloud, which is probably gravitationally interacting with the Pisces Dwarf Galaxy, no stars have been detected. And yet, it has a diameter of 20,000 light-years. What's more, HVC 127-41-330 could be 80% dark matter. So, according to American astronomer Josh Simon, it could be the first dark galaxy observed in the universe. A dark galaxy is a hypothetical type of galaxy that is devoid of stars, or at least produces very few of them. If their existence is confirmed, these galaxies would be extremely difficult to detect, as they would be totally obscure. Theoretical models of galaxy formation suggest that dark galaxies are the first stage in the long process of galaxy formation. Observing one would be a giant step towards understanding the formation of our own galaxy. Although the Andromeda Galaxy's satellite galaxies, a dozen or so, are, like the Pisces Dwarf Galaxy, closer to us than the Andromeda Galaxy itself. Let's start with NGC 185, a spheroidal dwarf galaxy that you'll also see under the name Caldwell 18. Discovered in 1787 and recognized as a member of the local group in 1944, this galaxy is located 2.1 million light-years from us in the constellation Cassiopeia. It appears to be gravitationally linked to NGC 147, or Caldwell 17, another spheroidal dwarf galaxy and companion of the Andromeda Galaxy. The two form a stable binary system. At the same distance from the Andromeda Galaxy as the Triangulum Galaxy is the irregular dwarf galaxy IC10. Located 2.15 million light-years from us, it belongs to the Cassiopeia constellation. Discovered as a celestial object in 1889, it was not identified as a galaxy until 1935. It was Edwin Hubble once again who hypothesized that it belonged to the local group. This was confirmed in 1966 by the measurement of its radial velocity. Smaller than the Small Magellanic Cloud, it is nevertheless as luminous as that galaxy. Its active star-forming phase lasts longer than that of the Small Magellanic Cloud, so there are several generations of stars in this galaxy. On the other hand, it is rapidly consuming its reserves of interstellar gas, which will certainly be exhausted in just a few billion years. This galaxy continues to amaze scientists, as it is also home to one of the most massive stellar black holes known, with a mass several dozen times that of the Sun. Around 2.3 million light-years away, we also find the Andromeda 2 Galaxy, a spheroidal dwarf galaxy discovered in 1972, along with other galaxies named Andromeda 1, Andromeda 3, and Andromeda 4. Like the Pisces Dwarf Galaxy, Andromeda 2 is located between M31 and M33, so it's not clear which galaxy it's a satellite of, but scientists are leaning towards the Andromeda Galaxy. Andromeda 3, 2.5 million light-years away, is also a spheroidal dwarf galaxy. No stars are thought to be forming in this galaxy, as it contains only old stars, either the same age as those in the Milky Way, or some 3 billion years younger. On the other hand, 56 variable stars have been identified. Irregular dwarf galaxy IC 1613, located roughly between Andromeda 2 and Andromeda 3 in the Cetus constellation, has the shape of a spiral galaxy, but the characteristics of both irregular and spheroidal galaxies. It contains very little cosmic dust, making it easy for astronomers to probe its contents. On the other hand, it is very dim, so you won't be able to observe it with the naked eye. We're still 2.5 million light-years away. You can also see the Andromeda 7 Galaxy, also known as the Cassiopeia Spheroidal Dwarf Galaxy, which was discovered in 1998. This galaxy is interesting because it is the brightest and most massive of all the spheroidal dwarf galaxies that are satellites of the Andromeda Galaxy. It also has the highest metallicity. Its stars are rather old, with 90% of them having formed 5 billion years ago. Not far away is M32 or NGC 221, an elliptical galaxy that is also made up mainly of old stars and has therefore not experienced a period of star formation for a long time. Scientists believe that M32 was originally a spiral galaxy that crossed the galactic disk of the Andromeda Galaxy. It would then have lost most of its peripheral mass. It shows signs of a supermassive black hole at its center. Also nearby is the Whale Dwarf Galaxy, a low-brightness galaxy, like most spheroidal dwarf galaxies. However, it is not a satellite of the Andromeda Galaxy. Indeed, this galaxy is too far away to be a satellite, so it's referred to as an isolated spheroidal dwarf galaxy. These galaxies are quite rare in the local group, but the Whale Dwarf Galaxy is not the only one. The Toucan Dwarf Galaxy, for example, is also an isolated spheroidal dwarf galaxy. Analyses carried out with the Hubble telescope have enabled scientists to establish that for 8 billion years, there has been no star formation in this galaxy. Four other satellite galaxies of the Andromeda Galaxy are located further away from us than M31. These are Andromeda 1, Andromeda 5, M110, and Andromeda 6. Andromeda 1 was discovered at the same time as Andromeda 2, 3, and 4. This spheroidal dwarf galaxy is located 2.6 million light-years from us and 150,000 light-years from the Andromeda Galaxy. It is the least luminous galaxy, in which a globular cluster has been found. Andromeda 5 was discovered 25 years after the first 4 Andromeda galaxies. It is an unremarkable dwarf spheroidal galaxy, except for its high metallicity. M110, or NGC 205, 2.7 million light-years away, is more interesting to scientists. This elliptical galaxy contains unusual levels of molecular and ionized gas and dust. What's more, its stars follow random motions, while the galaxy itself is animated by a rotational motion. Several globular clusters have been detected in this galaxy, all of which contain old stars, except the one near the galaxy's heart. The last satellite of the Andromeda Galaxy, Andromeda 6, also known as the Pegasus Spheroidal Dwarf Galaxy, is thought to be located 3.1 million light-years from M31, and not 2.7 million light-years away, as has long been thought. It should not be confused with the irregular Pegasus Dwarf Galaxy, DDO 216, which is also a satellite of M31 in the Pegasus constellation. Let's go back a little further to 2.8 million light-years away, where we find the Toucan Dwarf Galaxy we mentioned earlier. This spheroidal dwarf galaxy is unusual in that it is neither a satellite of the Milky Way nor of the Andromeda Galaxy, like the Whale Dwarf Galaxy. What intrigues scientists is that it lies almost opposite the other members of the local group in relation to the Milky Way. Unlike other isolated spheroidal dwarf galaxies, the Toucan Galaxy is not currently undergoing a period of star formation. In fact, this galaxy appears to be gas-free. It is thought to have been star-forming for around 1 billion years, 13 billion years ago. For the last 8 billion years, no new stars have formed. In fact, the Toucan galaxy is thought to have approached the Andromeda Galaxy around 11 billion years ago, ejecting it far out to its present position. Such galaxies are known as counter-current galaxies. "3 million light-years away, the Wolf-Lundmark-Melotte WLM Galaxy is an irregular barred dwarf galaxy that is not a satellite of either the Milky Way or the Andromeda Galaxy. It is located in the Whale constellation. It had already been observed in 1909 by German astronomer Max Wolf, but was not classified as a galaxy until 1926 by Swedish astronomer Knut Lundmark and British astronomer Philbert Jacques Melotte, hence its name. Half of the stars in the WLM galaxy are over 9 billion years old. However, between 1 and 2.5 billion years ago, star formation resumed, particularly in the bar, so there are also young stars in this galaxy. Stars are currently forming in this galaxy. Because it lies at the edge of the local group, the Wolf-Lundmark-Melotte Galaxy has been relatively protected from mergers and interactions with other galaxies, making it an interesting one to study. The Dwarf Aquarius Galaxy, also known as DDO 210, is another isolated irregular galaxy, located 3.3 million light-years from us. It is in fact part of a group of irregular galaxies that do not appear to belong to any particular subgroup. This galaxy is of interest to scientists because it shows a blue shift. The blue shift is different from the red shift, which you've probably heard of. In a nutshell, the red shift is the spectral evidence emitted by celestial objects that are moving away, such as galaxies, but also planets. Redshift is one of the evidences of the expansion of the universe. Well, the blue shift is the opposite phenomenon. The blue shift is spectral evidence that objects are moving closer to us. The Andromeda Galaxy, which is approaching us and will collide with the Milky Way in a little over 4 billion years' time, shows a blue shift. The same applies to the Dwarf Aquarius Galaxy. It is approaching our solar system at a speed of 137 kilometers per second, or 185 miles per second. The Dwarf Aquarius Galaxy is one of the few local group galaxies for which we can rule out a past proximity to the Milky Way or M31. In other words, based on its current position and velocity, scientists have deduced that it has not in the past been located close to one of the two most massive galaxies in the local group. Like the Wolf-Lundmark-Melotte Galaxy, the Dwarf Aquarius Galaxy still contains significant quantities of hydrogen, enabling it to support star formation, albeit at a relatively low level. The median age of stars in this galaxy is 6.8 billion years. This makes it the galaxy in the local group with the youngest median age of stars, after the Leo A galaxy. For this reason, scientists have speculated that the late star formation may be linked to the galaxy's isolation. Do you remember that we observed the Sagittarius dwarf galaxy earlier on this trip? This satellite galaxy of the Milky Way is the second closest to us, after the Big Dog Galaxy. We're now looking at the irregular dwarf Sagittarius galaxy, not to be confused. The first, 80,000 light-years away, is elliptical or spheroidal. The second is irregular and lies 4.2 million light-years from us, i.e., very close to the borders of the local group. In short, one is very close to us, the other very far away. The irregular Sagittarius dwarf galaxy was discovered in 1977. As it is very close to the local group boundary, we don't really know for sure whether it belongs to this group of galaxies. In any case, if it does belong to the local group as we assume, it's the farthest local group member galaxy from its center of gravity. Far more luminous than the dwarf Aquarius galaxy we've just observed, it would have experienced a longer period of star formation and possesses a large number of intermediate-age stars. Most of the stars in this galaxy would therefore be between 4 and 8 billion years old. Just 4.2 million light-years away, another galaxy is located on the outskirts of the local group in the Big Dipper constellation, UGC 4879. This is one of the most isolated galaxies in the local group. It is an irregular dwarf galaxy. It is separated from its nearest neighbor, the Leo A galaxy, by 2.3 million light-years, the distance between the Milky Way and the Andromeda Galaxy. It would seem, however, that this galaxy is getting closer to us. UGC 4879 behaves strangely, intriguing astronomers. The vast majority of its stars formed during the first 4 billion years after the Big Bang. Nothing happened for the next 9 billion years until fairly recently, when star formation resumed. In any case, analyses of this isolated galaxy have shown that it probably contains dark matter and a stellar disk. This solitary galaxy has not interacted with other galaxies, making it particularly interesting material for astronomers seeking to understand the complexity of star birth in the universe. When we were looking at the Lion A galaxy earlier in this journey, we mentioned the Antlia-Sextans group. Now that our journey is drawing to a close, it's time to take a closer look. The Antlia-Sextans group is a small group of galaxies located in the Hydra, Sextans, Leo, and Pneumatic Machine constellations. On average, it lies 4.3 million light-years from us, at the very edge of the local group. For this reason, this group of galaxies is sometimes considered to be outside the local group. Many researchers say that the Antlia-Sextans group is an independent group. This group of galaxies includes NGC 3109, the Sextant A and B galaxies, the Leo P galaxy, and the Pneumatic Machine dwarf galaxy. Let's start with NGC 3109. This small, barred Magellanic spiral galaxy, 24,000 light-years across, is located in the Hydra constellation, some 4.35 million light-years from us. It's a so-called low-surface brightness galaxy, meaning that seen from Earth, its brightness is less than 1 magnitude lower than that of the night sky. So far, so good. Most dwarf galaxies are low-surface brightness galaxies. NGC 3109 does, however, have some original features. It has a very low metallicity, like the Small Magellanic Cloud, and contains an unusually high number of planetary nebulae for its low luminosity. A planetary nebula, which is in fact nothing like a planet, is a large cloud of gas created by a giant star at the end of its life, which becomes unstable and starts ejecting its upper layers. Planetary nebulae are magnificent celestial objects with beautiful colors. Analysis of the radial velocity of the disk deformation of galaxy NGC 3109 has shown that this galaxy and the Dwarf Pneumatic Machine Galaxy came closer together around 1 billion years ago. These two galaxies of the Antlia-Sextans group are thought to be in a tidal gravitational interaction. The Pneumatic Machine Dwarf Galaxy is located 4.17 million light-years from us in the constellation of the Pneumatic Machine, as its name suggests. It is sometimes classified as a spheroidal dwarf galaxy, sometimes as a spheroidal to irregular transitional dwarf galaxy, and sometimes as an elliptical dwarf galaxy. It contains stars of varying ages, with the youngest concentrated in the center and the oldest on the periphery. The Antlia-Sextans group also includes the Sextant A galaxy, an irregular galaxy 5,000 light-years across with a distinctive square shape. At least it's the square shape it appears to us from Earth. The Sextant B galaxy, which forms a pair with the Sextant A galaxy, is also an irregular galaxy. It lies just outside what is considered the boundary of the local group, and is moving away from the Milky Way at a speed of 300 kilometers per second, or 186 miles per second. It is one of the smallest galaxies in which planetary nebulae have been observed. At least 5 have been identified. Finally, the Leo P galaxy is a small irregular galaxy in the constellation Leo. It is very distant, around 5.3 million light-years from us. When it was discovered in 2005, scientists thought it was a high-speed cloud. It wasn't until 2013 that its nature as a dwarf galaxy was confirmed. The Leo P galaxy is home to one of the most metal-poor environments in the local universe, with a very low metallicity of just 3% that of the Sun, and stars containing 30 times fewer heavy elements than the Sun. In fact, the Leo P galaxy is similar to primitive galaxies. It is one of the smallest and faintest star-forming galaxies in the local group, with a total luminosity 440,000 times less than that of the Sun, and a stellar mass only 560,000 times that of the Sun, which is low. It therefore contains relatively few stars. And yet, it's one of the few galaxies in the local group, or in its immediate vicinity, if you consider that it's not part of it, that is currently still forming stars. Does that surprise you? The truth is, its star formation rate is very slow, equivalent to 1 solar mass every 20,400 years. No wonder then that it contains so few stars, even though it has been forming stars steadily for at least 4 billion years. We've now completed our tour of local group galaxies. However, it's important to remember that the local group isn't all galaxies and stars. Let's explore the local group's remarkable objects. Let's start with the Smith Cloud. Does the name ring a bell? It's a high-velocity gas cloud with a mass 1 million times that of the Sun. High-speed gas clouds like the Smith Cloud are of vital importance in the local group. When they fall into the disk of a galaxy, they add baryonic matter to the already diluted matter present in the disk. Baryonic matter is made up of composite particles known as baryons. More concretely, Baryons are the electrons and protons that make up the atoms of all observable molecules and structures in the universe. Stars, for example, are made up of baryonic matter. You can see where we're going with this. High-speed clouds, by adding matter essential for star formation to galaxy disks, will help maintain the galaxy's star formation rate. The Smith cloud is traveling at 870,000 kilometers per hour, or 540,000 miles per hour, towards the Milky Way. It is therefore expected to collide with our galaxy in around 27 million years' time, well before the predicted collision with the Andromeda Galaxy. This impact could trigger an explosion of star formation. The most recent studies of the Smith cloud suggest that it formed on the periphery of the Milky Way before being ejected some 70 million years ago. But scientists still don't know how this happened. The Magellanic Current is another notable high-speed cloud of the local group. This is the matter bridge in the wake of the large and small Magellanic Clouds. It moves at a speed of 400 kilometers per second, or 250 miles per second, well above the speed at which our galaxy is moving. We don't really know how it formed, but it's assumed that tidal forces between the Milky Way's two satellite galaxies are behind it. In 2010, it was established that it would cover a distance of 600,000 light-years, which is much longer than researchers had previously thought. From this information, scientists have deduced that the Magellanic Current may have formed around 2.5 billion years ago, when the Magellanic Clouds passed close to each other. The Magellanic Current is of interest to scientists who study it to better understand the interaction of high-speed clouds and our galaxy. Before ending this journey, let's take a look at one last unusual local group object, known as the Unicorn Ring, or Unicorn Current. We already caught a glimpse of it earlier during our exploration of the Big Dog Galaxy. This long filament of stars discovered in 2002 surrounds the Milky Way over a length of 200,000 light-years at a distance of around 53,800 light-years. We don't really know the origin of the Unicorn Ring. It could be the remnants of the merger of two galaxies, either the merger of the Dwarf Great Dog Galaxy with the Milky Way, or the merger of the Dwarf Sagittarius Galaxy with our own. In any case, according to a 2011 publication in the respected journal Nature, the merger of the Milky Way and the Sagittarius Dwarf Galaxy could create such rings. Another hypothesis asserts that the Unicorn Ring is not actually a ring, but simply an overdensity. Overdensities are said to be common in galaxies with distorted flaring disks, such as the Milky Way. In other words, this is not an independent structure, but a ripple in our galaxy's disk. This hypothesis was invalidated by observations made by the Anglo-Australian telescope in 2007. According to these observations, a deformed disk could not create the structure we observe. For that to happen, the disk would have to erupt, or the cause could be external to our galaxy. In short, we don't know much more at present, but scientists are continuing to investigate the origins of this original local group structure. Our journey is drawing to a close. It's tempting to explore the universe even further. You're probably wondering what lies beyond the local group. Our neighboring galactic group is the IC 342 Maffei group, which has the same structure as the local group. In other words, it's made up of two structures organized around massive galaxies. The first is IC 342, or Caldwell 5, an intermediate spiral galaxy in the Giraffe constellation, 11.4 million light-years from us. The second is actually a pair of galaxies, Maffei 1 and Maffei 2, both located in the Cassiopeia constellation. Each of these two structures has 9 known satellite galaxies. Like the local group, the IC 342 Maffei group is part of the Virgo supercluster. The local group and the IC 342 Maffei group are only a tiny part of our universe. There are many other groups, such as Stephan's Quintet, a group of 5 galaxies located in the Pegasus constellation and remarkably photographed by the James Webb Telescope, or Robert's Quartet, a group of 4 galaxies in the Phoenix constellation. And in a few billion years' time, all this will have changed again. The dynamics of the local group itself are changing, albeit on such a large timescale that we don't realize it. With the merger of its 2 main galaxies, the local group will look decidedly different in 4 billion years' time. In place of the 2 substructures of our galaxy group, we'll have a large elliptical galaxy, whose other nearby galaxies, notably the Triangulum Galaxy, will become satellites. It's also possible that the local group will one day merge with the Virgo cluster, the nearest large cluster of galaxies. But we're talking here about a future where the Earth will probably no longer exist, devoured by our sun, then transformed into a red giant. In the meantime, we have plenty of time to continue observing the local group and its surroundings, and to learn a little more every day about the universe and its formation.